There's time for 5 minutes of questions, and we'll see how that goes. Let's get started so we don't cut anybody short. We're going to start with Dan Michael.
Okay, good afternoon, everyone. Thanks for sticking with us this late in the day. So I'm going to begin my presentation by giving you a timeline of some of the relevant scientific background behind NVG 291. There we go. So for more than a century, it's been known that there's limited axonal growth through the scar that forms after a spinal cord injury. In 1990, chondroitin sulfate proteoglycans were, for the first time, shown to be upregulated in the matrix of the glial scar and to inhibit neural repair mechanisms. In 2009, protein tyrosine phosphatase sigma, PTP sigma, was identified as a receptor for these proteoglycans and was shown to mediate their inhibitory effects on repair. And then in 2015, Jerry Silver's lab at Case Western Reserve developed a PTP sigma peptide mimetic therapeutic, which they termed intracellular sigma peptide, or ISP. ISP has sequence derived from the, I can't really see this laser, it's in purple. It has sequence derived from the intracellular wedge domain of rodent PTP sigma. And Dr. Silver's lab tested ISP in preclinical models and showed that it could promote axonal regeneration, plasticity, and remyelination, and more importantly, in animal models of both acute and chronic spinal cord injury, showed that it could promote functional recovery. Now, NVG 291 is the human analog. It has really the same structure. It differs by just a single amino acid in the wedge domain sequence. I'm showing you just two representative studies, an acute study on the left and a chronic study on the right. So on the left is an acute thoracic injury model where ISP was initiated 1 day after injury. On the right is a chronic cervical injury model where treatment wasn't initiated until 3 months after injury. And because we're looking at different models, thoracic on the left, cervical on the right, we have different outcome measures. On the left, the BBB scale is more a measure of mobility, and on the right, the forelimb locomotor rating scale is a measure of forelimb and digit function. But both of these studies show that there's significant functional recovery, motor recovery in the rats that received the peptide compared to vehicle alone. And results like this have been replicated by independent investigators. And the focus has always been on evaluating motor recovery. A couple of the studies also looked at bladder function and did show improvements in bladder function. One of those studies is shown here, where ISP was demonstrated to dose-dependently improve bladder function. Okay, but that's the animals, and now we're talking about moving into people. So I think I went through it too quickly, but on one of the previous slides, we did complete a phase 1 trial in healthy subjects just last year. And this showed that NVG 291 was tolerated and safe across a range of doses in healthy participants. So with that in mind and the preclinical efficacy data that I summarized, we transitioned towards thinking about study design for our first proof of concept trial. And really, there are three main hypotheses that we wanted to take in our approach to clinical translation. First hypothesis is that NVG 291 might be effective in either subacute or chronic injury, or both, because of the preclinical data. Secondly was that NVG 291 might improve connectivity, as was shown in preclinical studies, but moreover, that we can actually measure this improved connectivity electrophysiologically. And third, our third hypothesis is that we felt we would be most likely to be successful in clinical translation if we were to enroll a motor incomplete population. Why? Because the animal models are motor incomplete models. This slide summarizes the study design for the trial that is ongoing. It's a single-center trial being conducted at Shirley Ryan Ability Lab in Chicago. And the rationale for a single-center design is that this allows for uniform assessments and training, and this can reduce variability. What's most important is reducing variability of the electrophysiological measurements, which, as you'll see, we're leveraging quite heavily in the study. So if we were to include multiple sites, it would be more difficult to standardize the approach to electrophysiological measurements, but because we have a single center, we can leverage the fact that we have the same small number of assessors, we have the same training, we're using exactly the same equipment for all visits, all subjects throughout the 16-week trial. So in the trial, we are measuring clinical and electrophysiological assessments, and there's also training of the upper extremities, alternating with lower extremities 4 to 5 days a week. And over the 16 weeks, there's study treatment, either NVG-291 or placebo, over the first 12 weeks, and the last 4 weeks have no intervention. So the study is really 2 studies in one. We're enrolling 2 separate cohorts, chronic and subacute, about 20 subjects each. Chronic is defined as 1 to 10 years post-injury, subacute 20 to 90 days post-injury. Some of the key eligibility criteria are shown on the slide. This is a motor incomplete population, and we define a minimal and maximal level of function in the hand and lower extremities for each of these cohorts. But we also require that there be evidence of electrophysiological connectivity in 2 specific qualifying muscle groups, tibialis anterior, TA, and first dorsal interosseous, FDI. And we do that because it's related to our co-primary endpoints, as I'll get to on this slide. But first, I'll just make the point that we are looking at 10 muscle groups in all with different types of electrophysiological assessments. But really, our focus is on the 2 qualifying muscle groups I mentioned, FDI and TA, where we require that there is a measurable motor evoked potential in these 2 muscle groups at baseline. So our primary objective is to evaluate the change in cortical-spinal connectivity, and our co-primary endpoints are the change in normalized motor evoked potential amplitudes to the TA and the FDI. So we have a range of secondary and exploratory endpoints and objectives. 7 secondary clinical objectives shown on the slide. We're looking at change in motor scores, as you can see at the bottom. The other 5 endpoints are based on performance tests. Performance tests mostly of the hand, but also we're looking at change in 10-meter walk test speed. And these were included really because I think they're, for the most part, continuous scales, and it can give you more precision if you're trying to detect motor recovery, and increases the statistical power than if you were to use, for example, ordinal or categorical scales. Now we have other electrophysiological objectives shown at the top right. We're looking, for example, at change in latencies. There is evidence from preclinical studies that the peptide can promote remyelination. If this effect were to occur in humans, this might be reflected in a shortening of the conduction time. So that's why we're looking at that. We have additional clinical outcome measures shown to the bottom right, exploratory, and we're also looking at advanced imaging metrics of the spinal cord and brain. This slide is showing you the blinded, the study is still ongoing, of course, blinded baseline clinical and demographic characteristics for the first 17 subjects randomized. Again, the target cohort size is 20. And so just quickly, the average age is about 47 years, about 80% male, Time since injury is about 4 years. The range is 1 to 10. Neurological level of injury is C7 and higher. You can see the distribution. And these are age impairment scale C and D individuals. I won't go through the remaining rows, but I think what you see in the table just underscores that this is a motor incomplete population with impairment in motor function both of the upper and lower extremities. I will point out that of the 17 subjects that are in this table, 2 of them at baseline could not walk 10 meters, and 3 of them could not complete the 9-hole peg test with either upper extremity. So in closing, I showed you sort of a summary that preclinical models of spinal cord injury have demonstrated that the rodent version of MVG-291 can promote functional recovery. We're now trying to translate into humans. Our ongoing clinical trials involving these 2 cohorts. The chronic cohort is very much nearing completion of enrollment, and the subacute cohort will be commencing enrollment shortly. It's a motor incomplete cohort. We are evaluating a range of both clinical and electrophysiological assessments. And I think what makes the study different is that we are leveraging electrophysiology quite heavily, both to define the eligible population, but probably more importantly to define efficacy endpoints. And we're doing that because we feel it's a sensitive objective marker of recovery, and including it in this proof of concept trial maximizes the probability of both detecting and characterizing an efficacy signal with NVG-291. I think a higher probability than we could probably achieve with clinical measures alone. Thank you, and I'm happy to take any questions. Yes, so it's a subcutaneously administered peptide once a day. So over the 12 weeks of the 16-week trial, it's given once a day as a subcutaneous administration and rotated. Abdomen, arms, thighs. It's rotated, yeah.
Where does your confidence come from that this will work? When you see the animal models, there have been many animal models, and did you, for example, try in vitro, like human cells, or something?
Well, the big question, this is clinical translation. There have been a lot of things that have worked in preclinical studies and it hasn't translated, and the question is why. And that's the subject of a whole day conference at least. But we have efficacy in animals, rat models, acute and chronic, and the peptide we're using, MVG-291, it's very similar to ISP. It just is the genetics are slightly different. It's one amino acid difference. But this is clinical translation, and we don't have any evidence that it works in humans, and that's why we're taking a pretty cautious approach, including electrophysiology, to try to learn from this study. If it's a small study, these are small cohorts, and if we don't see clear-cut clinical evidence, we're looking for electrophysiological change to teach us something.
Thank you. So we will move on to the next speaker, and if everyone keeps on time, we'll actually have 5 minutes for questions. So if you have questions, Dr. Michael and Dr. Felix will take